Welcome to Spring LIB.
This is the answer to Chapter 12, problem number 17 from the Smith Organic Chemistry textbook. And this problem asks us to draw the products formed when both cis and trans-2-butene are treated with a peroxyacid followed by hydroxide ion and water. And then we're asked to explain how these reactions illustrate that anti-dihydroxylation is stereospecific. Okay, and so the first thing to do, I guess, is to draw the products of these reactions. And so we should remember that using these reagents, so a peroxyacid followed by a hydroxide ion and water is going to give us an anti-addition, an anti-dihydroxylation. So to each of these molecules, we're going to add two hydroxy groups, and they're going to be added in an anti-fashion. So for the first one here, for cis-2-butene, that's going to look like this. So we still have our carbon-carbon single bond here instead of the double bond. These hydrogens will still be just as they were, although actually... So one way to draw this to make it easier is to perhaps first add the OHs that we're going to add, and to add them top and bottom like this, so that they are, we're showing that they're anti to one another. And then we can sort of shift our other substituents around a little bit in order to accommodate that. So our hydrogen is still wedged, our methyl groups are still dashed, but we've moved them a little bit to show that these hydroxy groups are anti to one another. So we're also going to get the enantiomer of this. So everything is going to be the same, except, as I said, this is going to be the other enantiomer. So this time, this hydroxide will be down, this hydroxide will be up. But again, the other parts of this molecule are going to be unchanged. So still wedged hydrogens and dashed methyl groups. Okay, and so these two molecules, the stereo relationship that these two molecules have with one another is that these are enantiomers. So when we do an anti-dihydroxylation on cis-2-butene, we end up with this pair of enantiomers. So when we do the same anti-dihydroxylation on trans-2-butene, we only get a single molecule. So we put this OH group up and this OH group down. And then again, our other groups are not going to change. Okay, and so if we were to draw the other product here, it would actually be the same exact molecule, but flipped and rotated 180 degrees. And so this is the only product here. And this is a meso compound. Okay, and so for part B of this question, we're asked, how does this prove that, well, let me read it. So we're asked, explain how these reactions illustrate that anti-dihydroxylation is stereospecific. Okay, and so this proves that because we started with different stereoisomers. Oops, stereoisomers. Okay, so we started with different stereoisomers, and we are ending with different products. And so this proves that that this reaction is stereospecific, because we would expect to, if it wasn't stereospecific, we would expect that even if we started with the two different stereoisomers of the starting material, we would expect the products in each case to be a mixture of all the possible products. And they're not. A particular stereoisomer of a starting material gets us a particular product or set of products, whereas the other stereoisomer gets us a different set of products. And so that proves that this reaction is stereoselective. And that's the answer to chapter 12, problem number 17.